Good morning, all the students. Let's start our fourth lecture under this module 4. Even this has some mathematical concepts. I think overall, when we compare to other modules, this module has more mathematical concepts. But if you focus, it will be easy to understand. All are direct derivations, and they're not even complex also. So you can easily follow. Just stay focused. In the last class, we have seen what is maximum likelihood and the least square error hypothesis. Today, we are going to connect how predicting probabilities is related to maximum likelihood hypothesis. You know what is maximum likelihood hypothesis, right? We have derived that HML is sigma H belongs to H, probability of D given H, right? This is called as the maximum likelihood hypothesis, and how it is used for predicting the probabilities we are going to see. Now consider the setting in which we wish to learn non-deterministic non-deterministic or probabilistic function f such that x maps to 0, 1, which has two discrete output values. What do we mean by this? What is non-deterministic? Non-deterministic means we can't determine exact occurrence of something. Say, if I toss a coin, I can't say whether head will occur with 100% confidence or tail will occur with 100% confidence. Then I say my experiment here is, my coin toss experiment here is non-deterministic. Whereas when I calculate your height and weight, when I measure your height and weight and calculate the body mass index, that is BMI, I can do that with 100% confidence because I have a particular formula for that to calculate BMI based on height and weight, right? That is called as deterministic calculation. Whereas in non-deterministic calculation or non-deterministic approach, we can't determine the outcome with 100% confidence. It always has a chance. That is why we say it, we call it also as probabilistic approach. Okay, probability means you are talking about a chance. Yes, whenever your friend asks you to attend some party, I probably may not come, you say. What is the probability? There is a chance of coming or not coming, right? You can't completely confidently say that you can attend the party. In that case, we say that your decision is non-deterministic. You can't say something with 100% confidence. Did you understand clearly? Now, consider the setting in which we wish to learn a non-deterministic function. Here we are trying to learn a non-deterministic function, f defined as x that is mapped to 0, 1, which has two discrete output values. So the discrete output value, say positive, the patient is tested as positive or he is tested as negative. The customer is predicted to be fraudulent or not fraudulent. The insurance claim is fraudulent claim or not a genuine claim. If the customer is reliable or not reliable. These are discrete output values, right? So we have some, if you want to predict some categorical value as the outcome variable, in that case, how you are mapping the instance set. Any of the instance means any of the training examples output should be a category here, 0 or 1, yes or no, defaulter or not, like that. Okay, in that case, if we take the probabilistic approach, then what we can do is, say, if you determine if you decide a threshold of 0.5, say, now all the values, all the training examples predictions that fall below 0.5, you can assign it to negative class, that is 0. And all the training examples probability values, if they are falling, the prediction values probability, if it is falling above 0.5, then you can assign it to positive class, that is 1. That is called as non-deterministic approach or probabilistic approach. Means whenever you are assigning a data point or a training example to a particular class, you are doing it with some probability. You are doing it with some likelihood, right? So if you have two classes, star and circles, now a new data point circle is given. Now that circle's likelihood of falling into this star category is 0.2 and it's falling into circle category, say it is 0.8. Now into which class do you assign? Obviously to 0.8 probability class, because it is having high likelihood of belonging to that particular circle class. It has high chances of falling into that circle class. Did you understand now? In this way, this notion, this idea, we are applying in this maximum likelihood hypothesis for predicting the probabilities. We are predicting the probabilities, assigning a threshold, and below that threshold, you are assigning to one class, and above that threshold, you are assigning it to another class. Now, when we take in this example a circle data point, now if it is having maximum likelihood of falling into this circle class, it is also that it is reducing its likelihood of falling into star class. It is the magic of English that we are actually attaching to this mathematics. Did you understand? I am saying the data point, the circle data point, its likelihood, if it is increasing so that it falls into the circle class, then we can also say that its likelihood of falling into the star class is reducing. Correct? So if you have 0.2 likelihood for it to fall in star class and 0.8 likelihood to fall in circle class, we assign it to circle class. That is how probability will help the learner, a machine learning model, to assign a data point to a particular class with some given confidence. That confidence is provided by the probability of it falling into either one class, a class, or the other class. Did you understand clearly now? Now read the first point, it will be very clear for you. Consider the setting in which we wish to learn a non-deterministic function. Non-deterministic function means you don't have confidence in the outcome, but probability, if you assign to it, you will get some confidence. For that, how the function is first of all defined, let us see. F is defined as x, any instance outcome should be mapped to either 0 or 1, which has two discrete output values. Now let us take an example, it will be more clear to you. For example, among a collection of patients exhibiting the same set of observable symptoms, understand it carefully. Among a collection of patients, you have a group of patients exhibiting the same set of observable symptoms. All are having observable symptoms. And same, they are also same. The features are same. The symptoms of the disease are same. Under that scenario, we might find that 92% survive and 8% do not. Why is this uncertainty? All patients are having same set of observable symptoms. Then can't we say 100% of them are either surviving or they are not surviving? Why again there is percentage, limited percentage? 92% of them are surviving. 8% of the patients are not surviving the disease. Why? Why is that uncertainty associated? When the same set of symptoms are observable among the patients, then why only 92% of them are surviving and 8% are not surviving the disease? Why? This unpredictability could arise from our inability to observe all the important distinguishing features of the patient. In real time, you can't observe each and every distinguishing feature for a new data point, Means there are some points, there are some features which may not be observable. Say, if we take the COVID patient symptoms, they maybe there may be some symptoms which are associated to their genetic properties or genetic features, which can't be studied in depth and which might not have been noticed by the scientists, but still playing some important role in their survival with the disease. In such cases, we can say that there are some factors, there are some features which are actually unobservable or which may lead to unpredictability of the disease in some cases. That is why 92% of the patients we are able to observe according to what symptoms they are surviving. But same symptom patients, 8% of them are not surviving also. There is some uncertainty in the hypothesis. There is some uncertainty in the outcome. Why is it? Is because there may be some symptoms which are unpredictable, which are unobservable. Okay, so this unpredictability could arise from our inability to observe all the important distinguishing features of the patients. That is why we are not confidently stating that 100% of the patients with these symptoms will survive. We are always taking a chance of only 92% are surviving, and we have a doubt with 8% of the patients. There is uncertainty in your statement. That is because you can't cover each and every feature of the patient in the real time. Got it? Now, given this problem setting, understand this problem setting now. Now, we might wish to learn a neural network or any other real valued function approximator. You can take other approximator like linear regression, ridge regression, lasso regression. When you start gaining expertise, no, not becoming, when you start gaining expertise in this particular field, then you will come across all these types of regressions. Regression problems are generally used for predicting real valued functions and classification problems for categorical values. Okay, now you'll come across all these types of regressions. It will be very, very interesting, I promise you. If you pursue a career in machine learning, actually, though in the beginning you have some hiccups like not understanding the mathematical concepts, but repeated effort if you put in this subject, it will start becoming very, very interesting. You can unveil, you can uncover lots of interesting concepts. Okay, so you just avoid your aversion to mathematics, that's all. If you avoid that, you will start understanding the beauty in this subject. Now, given this problem setting, given that there is uncertainty in prediction of something, we might wish to learn a neural network, or you can take any other model like linear regression, ridge regression, as I said, whose output is the probability that f of x equal to 1. Sorry. Yeah, whose output is the probability that f of x equal to 1. So if f of x equal to 1, then you predict it as a positive class. Or if f of x equal to 0, you predict it as a negative class. Or if you have any values in between, some probability you can associate with it. Now, in other words, we seek to learn the target function. How you can exactly model this is f dash. We are trying to learn the target function f dash such that each training instance's output should be either 0 or 1 or any value between them, if it is a continuous valued function. If it is a categorical valued function, then it is 0 or 1. That's all. No continuous values in between. Now, such that f dash x is equal to probability of that f of x equal to 1. Means if that training example's output equal to 1, then you can count it as that particular patient symptom have occurred. You have encountered a patient with that particular symptom. Okay, that is what you mean. Probability of f of x equal to 1. Now, You have a patient with some symptoms, but his outcome is 0. Then we say f of x is equal to 0. Means, though he have the symptoms, he is not surviving. If he is surviving, the value will be 1. If he is not surviving, the value will be 0. In that way, you have to understand. In the above medical patient example, if X is one of those indistinguishable patients of which 92% survive, then what is f dash of x? What is the probability? Remember, you're learning a real valued function. If it is a categorical function, you can take it as 1. But if it is real valued function, there is some probability associated with it. Then f dash of x is equal to 0.92. So in the given example, in the given medical patient example, if X is one of those indistinguishable patients, means all are having same symptoms. So the patients are indistinguishable. In that case, 92% survive. From the experiment, we got that 92% patients survive with those symptoms. Then what is f dash of x? What is the probability of f dash of x? It is 0.92. Probability lies between 0 and 1. That is why percentage will be converted to points, decimal points. So it is 0.92. Whereas the probability function f of x will be equal to 1. In this case, the probability function f of x will be equal to 1 in 92% of the cases. That is actually what we wanted to represent with respect to probability. Means when we say 92% of the patients are surviving and 8% of the patients are not surviving, we mean that the outcome of 92 patients out of 100 is equal to 1. They are surviving. And 8% of the cases, it is equal to 0. They are not surviving. That is how we need to connect probability and the functions. In this case, again, if it is classification, we say that 92% of the patients outcome is equal to 1. They are surviving the disease. And 8% of the cases, the outcome is equal to 0. They are not surviving. But if we take the continuous valued functions, we can say that it is 0.92. Now, what criterion should we optimize in order to find the maximum likelihood hypothesis for f dash in this problem setting? In this case, we must first obtain an expression for probability of D given H. Okay, what is probability of D given H? Probability of observing certain training examples, observing certain patients' data, given the hypothesis that 92% survive and 8% do not survive. Now you take a new data point. Is it in accordance with the problem statement that is made? The hypothesis that is made? That is probability of D given H. Now let us assume the training data D is of the form, observe this carefully. How is the training example format? X1 represents all the set of attributes and D1 represents the outcome. Say A1, A2, A3, A4. These are the attributes and D is the outcome. Now all these belong to X1 training example. Now X2 training example, again it will have separate values A1, A2, A3, A4. Separate values under A1, A3, A4. Right? Did you understand? X1 training instance, the first training instance, contains set of attributes and its outcome value D1. And second training instance X2 again has values under these attributes with outcome D2. That is generally represented as the set of all training examples D is equal to, how is it represented? It is a attribute value pair. What are the attributes represented by X1 and what is the value, the outcome value represented by D1 and so on up to XMDM, which has M training examples. This training example set has M training examples. That is why you have denoted up to XMDM, where DI is the observed 0 or 1 value for f of xi. Okay, the outcome may be either 0 or 1. Now, treating both xi and di as random variables. In the previous case, in Bayes' theorem, when we are calculating the posterior probability, we have assumed that all the training examples are related. That is why we haven't used x in calculating the posterior probability. We have just given P of D given H. But let us take in this case as xi also as random variable, means it may not belong to the same set of values. There is some uncertainty in the training examples which is leading to this 8% patients, they are not surviving though they are having the same symptoms. Okay, so the value is random here. You can't stick to same distribution in the attribute values. In that case, treating both xi, the set of attributes for a given training example, and di, the outcome for the given training example, as random variables. They are not static. That doesn't belong to same distribution. They are random variables, and assuming that each training example is drawn independently. What do we mean by this? Each training example is drawn independently means what? You are drawing one training example and selection of this training example doesn't affect the selection of the next training example. That is called as independent drawing of the sample or independent drawing of the training example. Okay, say if I toss coin 2 times, 2 coin toss experiment, I call it as 2 coin toss experiment. Now when I toss the coin for the first time, either head or tail may appear. Now when I am tossing the coin for the second time, the outcome in the first coin toss doesn't affect my second coin toss outcome. Did you understand? I'm repeating again. I'm performing a 2 coin toss experiment. I have 2 coins. Now I have tossed this coin. I got some outcome. Head or tail. Say I got head. Now getting head in this coin toss, does it affect my outcome in the second coin toss? Not at all. In that case, we call it as independent outcomes. One outcome doesn't affect the other experiment's outcome. That is called as independent outcome. So whenever you say that P of A and B are independent, then we represent it as the product of probability of A and probability of B. This is basic probability formula. If you say A and B are independent events, then probability of A and B is equal to product of probability A and probability B. Now, if you have mutually exclusive events A or B, mutually exclusive means I said already, if I toss a coin, then the appearance of head on the top excludes the appearance of tail on the top. So these two are mutually exclusive events. Occurrence of one event excludes the occurrence of other event, eliminates the occurrence of other event. That is called as mutually exclusive events. In that case, probability of A or B is the sum of probability A and probability B. Did you understand clearly? So whenever you are saying you are drawing a sample or training example independent of other draws, then the probability of one draw is multiplied with the probability of the other draw. Product, you have to say, you have to represent it as product of the individual draws. For that, this entire explanation I have given to explain you this formula. Now, treating both xi and di as random variables and assuming that each training example is drawn independently, we can write probability of d given h as probability of d given h is equal to product of, did you see here? For product, we are using pi symbol. For summation, you use sigma. But here, they are independent draws. When we say independent draws, then we have to calculate that their probabilities as product. That is why you have used pi. Pi I equal to 1 to m. You are using this probability of xi di given h. You are also considering xi here. Xi, comma, di, that is the outcome given the hypothesis. Outcome of that training example xi given the hypothesis. Did you understand? P of xi, the training example, comma, di given h. Initially you had just di given h. Now you are including xi also because you want to cover the uncertainty in the predictions. You want to explain the uncertainty in the predictions. That is why you are using P of xi, comma, di given h instead of simply di given h. Now it is reasonable to assume furthermore that the probability of encountering any particular instance xi is independent of the hypothesis h. Now we can assume this. Why? Because there are some patients which are not in compliance with the statement made. There are some patients, 8% of the patients, which are having the same symptoms but not recovering. For that, it is reasonable to assume, furthermore, that the probability of encountering any particular instance xi, that is the set of symptoms, for a patient is independent of the hypothesis h. Got it? Now, when h is independent of x, means that particular training instance is independent of the hypothesis, we can rewrite the above expression as, how we are changing that expression? Initially the expression is this. Now we can rewrite it as probability of di given h, comma, xi multiplied by probability of xi. Bayes theorem. Did you remember? Probability of h given d is nothing but probability of d given h multiplied by probability of h. Same concept you are applying here. You are rewriting the probability of d given h as initially it is probability of xi, comma, di given h. Now that you can rewrite by using Bayes theorem as probability of di given h, comma, xi multiplied by probability of xi. You want the prior probability of xi to use for the calculation of this probability of d given h. Why? Because xi is independent of the hypothesis. Okay? Mark this as your equation 1 because this will be using in later derivation. Now, what is the probability of di given h, comma, xi of observing di equal to 1 means what is the probability of di given h xi if the outcome is 1, if the outcome label is 1 for a single instance xi given a world in which hypothesis h holds. This notation is being read in this point, that's all. What is the probability of observing di equal to 1? What is the probability that this notation becoming 1 for a single instance xi, for a training example xi, given a world in which hypothesis h holds? There is some statement made that 92% of the patients survive with these symptoms. Now a new instance xi is given. What is the probability of its outcome being 1? That is this question. Now h is our hypothesis. regarding the target function, okay, which computes this very probability. So H is our hypothesis that is related to our target function, and that computes the exact probability what we want of observing this particular training instance and the outcome becoming 1. Therefore, probability of di equal to 1 given H comma xi for the training instance means for this training instance, given the hypothesis, what is the probability of the outcome becoming 1? Simply you can read like this. I'm repeating. Listen carefully. What is the probability of the training instance xi given this hypothesis, some statement about the disease? What is the probability of that patient surviving? Di equal to 1. Okay, that is nothing but H of xi. If he is surviving, it is according to the hypothesis, right? Means this xi is according to this hypothesis H. So simply you can represent it as H of xi. Or in general, you can represent it mathematically like this. This is more easy actually to understand. See, probability of di given H xi means what is the probability of this training instance becoming 1 given this hypothesis? It is nothing but H of xi. Because it is in accordance with the hypothesis, it is according to the hypothesis, it can be represented as H of xi. This xi training instance is according to this hypothesis statement made if di equal to 1. Correct? The patient xi is surviving means the outcome is equal to 1 means this training example or this patient is in accordance with the hypothesis made. That is why we are writing H of xi if the outcome is 1, if the patient is surviving. Now, if the patient is not surviving, then it is not according to the hypothesis. That is nothing but 1 minus H of xi. I'll make you understand this. Say, what is the probability of occurrence of an event? If we denote it with P, what is the probability of that event not happening? It is 1 minus P. Basic probability explanation, this one, right? The probability of occurrence of an event, if it is represented by P, the probability of that event not occurring is 1 minus P. In the same way, when that patient is surviving means that outcome is 1, then it is according to the hypothesis H xi. The training example is according to the hypothesis. So it is H of xi. If the patient is not surviving, then it is not according to the hypothesis. That is 1 minus H of xi. That is according to this explanation. Did you understand now clearly? If the patient is surviving, the event is happening, H of xi. If the patient is not surviving, 0, di equal to 0, outcome is equal to 0, that event is not happening. So it is 1 minus H of xi. I hope it is very clear now. Can we proceed further? Any doubts, students? Till here? In this representation? Okay. Now, in order to substitute this into equation 1 for the probability of D given H, let us first re-express it in a more mathematically manipulatable form. Let us express in more comfortable mathematical format so that you can easily understand why we have actually given this. I'll explain. It will be interesting if you stay focused. Concentrate here. Let us first re-express this in a mathematically understandable format. P of di given H xi. Again and again I am repeating, do not get bored. I want that terminology to be incorporated into your mind. Probability of a training instance xi, outcome di becoming 1 for the given hypothesis is equal to h of xi power di into multiplied by 1 minus h of xi power 1 minus di. Why did we write like this? Observe this notation what we have represented in the previous slide. P of di given h xi, if it is h of xi if di equal to 1. Okay. Now, if di equal to 1, what will happen to this exponent? Observe this. What will happen to this exponent when di equal to 1? 1 minus 1 will become 0. The power will become 0. So this entire term will become 1. So what is the probability when di equal to 1? H of xi. This power becomes 1. So it is h of xi. Right? So same, this whatever I have represented in this box, we are representing it in a more comfortable format. That's all. Now say if di equal to 0, what will happen? This term will become 1 because power, anything power 0 will become 1. This will become 1. Now in this case 1 minus di, that is 0, will be here this term power becomes 1. So it is 1 minus h of xi. So when di is equal to 0, the event is not happening. So it is 1 minus h of xi. If di equal to 1, then the event is happening. Then this term will be cancelled and you will have only h of xi. So this formula is another representation of this mathematical representation. Did you understand clearly? This formula is your maximum likelihood formula. Remember, it is very important. Now, if you understand this representation, it is very easy for you to derive actually. You need not even by heart or get confused what comes first, what comes next. Just understand what is posterior probability, what is prior probability, what is random selection from the training instances. All these terms, if you're very clear, you need not by heart, you can just write, it will flow out of your hand, whatever you wanted to write in the exam. Okay, let us use the above equation to substitute for P of di given h, comma xi in the following equation. Now we have this equation, right? We substituted Bayes' theorem for this and we have this equation, probability of D given H. We have this equation. Now into this equation, you substitute this formula. Now we write an expression for the maximum likelihood hypothesis as, what is maximum likelihood hypothesis? Something which maximizes the probability of occurrence of that event. That is why you are using argmax. Okay. Now, hypothesis, maximum likelihood hypothesis can be represented as argmax of all the hypotheses that belongs to hypothesis space, product of into this term, you are substituting this equation. Okay, that is h of xi power di multiplied by 1 minus h of xi power 1 minus di. Substitution is done and retain this term as it is. P of xi, retain that term as it is. Okay, now this is the representation for maximum likelihood hypothesis. Now let us see whether we can further simplify this representation. Now this is what we got after substitution. Now the last term is a constant independent of h. This last term is a constant, probability of xi, probability of a training instance occurring, probability of observing a particular patient data. It is independent of the hypothesis. Okay, but we are trying to relate it to the hypothesis, but initially in this case, the prior probability of it occurring is independent of the hypothesis. Now, do you think that some patient will come according to the experiment result what you have made, that 92% are surviving, 8% are not surviving? Now the patient who is coming have to survive so that he is in accordance with my hypothesis. Do you say like that? No. The patient comes and we have to refine our hypothesis actually. So when you take probability of observing a patient's symptoms of a patient coming to the hospital, it is independent of the hypothesis you have made that 92% survive and 8% doesn't survive. Did you understand? That is why the last term is a constant. We call it as a constant, independent of the hypothesis H. So it can be dropped. Let us make our formula more simpler by dropping that constant. Now it becomes maximum likelihood hypothesis is equal to argmax of the product of occurrence of the event and non-occurrence of the event. Now, the expression on the right-hand side of equation can be seen as a generalization of the binomial distribution. Did you study about this binomial distribution in your PUC? And that formula is same as this. If you can't recollect, after the class, just Google for binomial distribution, you'll understand. You'll recollect, not understand. You already understood how to represent this, right? So that is in accordance with the binomial distribution. Now, as in earlier cases, we will find it easier to work with the log of the likelihood yielding. Now, rather than using the entire term as it is, in order to make it more manageable, let us apply log so that the values will be brought down a little. If there are too high values, it will be brought down. Okay, so how to apply the log? Say if you have e power x, when you apply log to this, it becomes x into e, right? In the same way, you have not e, let us just take it as a power x. If you apply log to this, you will write it as x into a. X into log a. I'll rewrite this again. Yeah. If you apply log to a power x, then we can write it as x into log of a. Is it clear now? Okay. Now, log you are applying to this formula. So how do you get the terms? This exponent term comes to the beginning, di, log is represented by ln, this h of xi, log applied to h of xi, plus product will become plus when you apply log, you know that. Log of a into b is nothing but log of a plus log of b. That formula you know very clearly, right? So when you apply log to this entire term, this becomes log of h of xi di plus log of 1 minus h of xi 1 minus di. Now, when you apply the log, that exponent term comes to the beginning, as I said. Di log h of xi plus 1 minus di. This exponent term comes to the beginning. 1 minus di log 1 minus hi. H of xi. Now this above equation describes the quantity that must be maximized in order to obtain the maximum likelihood hypothesis in our problem setting. So in order to maximize the likelihood of this hypothesis, what has to be maximized? Either occurrence of this event has to be maximized to put it into a positive class, or the occurrence of this event has to be maximized to put it into a negative class. Okay. Now this result is analogous, means same as our earlier result showing that minimizing the sum of squared errors produces the maximum likelihood hypothesis in the earlier problem setting. In our previous topic, we have seen how reducing the prediction error and summing up all the prediction error squares, you will be able to, and minimizing that minimizing that value, you will get the maximum likelihood. HML is nothing but arg minimum of sum of all the predicted values minus the original output. Say O, squaring all of them. Okay, reducing this prediction error, minimizing that prediction error by arg minimum will give you the maximum likelihood. Means as much as you reduce the prediction error, the probability of that hypothesis becoming true with the training examples will increase. That is called as your maximum likelihood hypothesis. In this case, what we are doing, you're trying to maximize the occurrence of an event to put it into positive class, or non-occurrence of that event to put it into a negative class. Okay, the approach is the same. That is what they are trying to explain. Now in the next session, we'll see what is minimum description length principle. You remember Occam's razor method, what we discussed in neural networks beginning session. That can be further in detail discussed under this minimum description length principle. Why we prefer simpler hypothesis when compared to complex hypothesis. Any doubt here, students? Is the concept clear for you? If at all you get stuck somewhere, whenever deriving these notations or mathematical derivations, you just refer to the video, listen to the explanation, you'll easily understand. Okay? And I always want to say that you have to go through the videos 2 to 3 times. Mathematical notations can't be understood for the first time. In order to be comfortable with the derivations, you have to go through the concepts 2 to 3 times. Okay? Okay, we'll meet in the next class.